Hey, this is Avi Gutman with another Ask Me Anything event brought to you by quantreasoning.com. I invite you to join me live next time. We do this every Saturday at 11 a.m. Eastern, and you can attend for free by starting your free trial at quantreasoning.com. So, for a change, we don't have any free info in this data sufficiency question. And it actually looks like we do have free info because there's some text before the word what. But is that really free info? Not really. It's just saying, look, there's some random rectangle. We don't know anything about the rectangle. We want to know the perimeter. That's it. In general, what do you need to know in order to find the perimeter of a rectangle? Now, do you need to know the value of the length and separately you need to know the value of the width? Or is there possibly a way to answer the question without knowing the individual values of the length and width? It's not exactly right. There is a way, using the length and width, there's a way to answer the question without actually knowing the length and without actually knowing the width.
Maybe the sum of the two?
You got it, Eric. You got it.
Okay.
And that's a really, really important distinction when it comes to data sufficiency. Almost guaranteed, there will be a way to answer the question without knowing the individual values of the length and width, but instead knowing the sum of the length and width. And why would that be sufficient? Because the perimeter is twice the sum of the length and width. So just to put this in algebraic form in case that's useful to anyone, 2L plus 2W, so 2 times the length plus 2 times the width, that's the perimeter of a rectangle. And you can, of course, factor out the 2, and you end up with just the sum of the length and width. So if I am given the sum of the length and width, I can answer the question, because I'll just double it, and that's the perimeter. And I might not know the value of the length, and I won't know the value of the width, but I'll know their sum, and that would be sufficient in a question like this. So in many, many data sufficiency questions, where you just need to know some combination of two values, the sum, the average, the difference, the ratio, stuff like that, there will be a way to answer that question without actually knowing the individual values. And a lot of people get that wrong. So it's an important point to emphasize here. We just need to know the sum of the length and the width. I would also start with statement 2, just it seems easier. And I would ask the following. Does knowing the product of two values allow me to infer their sum? I'm abstracting this question with statement 2. Does knowing the product of two values allow me to infer their sum? We should be careful here because there is one more thing we know about these values, which is they're positive values. And I know that because it's geometry. So these are not just any random values, they're positive. Do they have to be integers? No reason to think that they're integers, but they do have to be positive. So let me put a finer point on my rephrase here. Does knowing the product of two positive values allow me to infer their sum? That's what this question is really asking. So what are some thoughts on that? No, that's right. Yeah, exactly. So if the product is a prime number, or if the product is 1, and we know that the values themselves are integers, then that would be sufficient. For example, if you know the product is 13, which is a prime number, and you knew the values were integers, then you know the values have to be 1 and 13, and then you can find their sum. It's 14. And that's why it was important for me to ask you earlier, do we know that these values are integers? Must they be integers? And you correctly said, no, there's no reason why they have to be integers. Now, in this case, also the product isn't a prime number, it's 48. So even if they were integers, it still wouldn't be sufficient. But that was a good point, whoever made that point, that if the product were a prime number, or 1, and we knew that the values were integers, then yes, that would be sufficient. One more thing I want to discuss about statement 2. Did you all know that the more symmetrical a shape is, the more area can be captured with the same perimeter? Did you know this? Let's get some intuition behind that rule. It's in the book, by the way. This is a really what I would call asymmetrical rectangle. And what would you call the most symmetrical rectangle in the world? There's a name for that kind of go ahead, Sword.
Square.
That's right. Here is the most symmetrical rectangle in the world, where the length is equal to the width, also known as a square. So now imagine they have the same perimeter. Can you tell that the more symmetrical shape managed to capture a lot more area within it than the less symmetrical shape? This is always true. If the perimeter is the same perimeter, the more symmetrical shape will capture more area within it. And what is the most symmetrical shape in the universe? Does anyone know?
Circle.
That's right, a circle. So if you were given a plot of land in the 18th century in the United States, when people were just given land for free, basically, right? I think you see that in the movie Gangs of New York. At the end of the movie, they have a race and they have to plant a flag, and that's how you get your plot of land, right? So if that happened, and the government said, okay, we're giving you, 1 kilometer worth of fence, and you can do with that fence whatever you want, and whatever area you can capture within that fence, within that perimeter of 1 kilometer, that's your land. If you wanted to maximize the amount of land that you can capture with that given amount of fence, with that given perimeter, you would put the perimeter in the shape of a circle. But what if the fence isn't flexible? It has to be straight lines. Then what would you do with a fence?
Octagon.
Exactly, a perfect octagon. Not just any octagon, a perfect octagon. Because if it's not a perfect octagon, you're wasting some area. But you know what would be even better than a perfect octagon is a perfect, I don't know what the name for it would be, but something with 30 sides, 30 equal sides, right? And then a bit less optimal would be a perfect pentagon. And a bit less optimal than that would be a perfect square. That's just called a square. And then a little bit less optimal than that would be a equilateral triangle. And a bit less optimal than that would be a non-equilateral triangle, right? Let's say a right angle triangle of some kind. And if you're already making a right triangle, at least have it 90, 45, 45. So it's at least a bit more symmetrical than, say, 90, 10, 80 or something like that. Okay? So that's something that I think is useful when we are evaluating statement 2, because we can then say, look, I know that a given area of a rectangle is going to lead to different perimeters depending on how symmetrical that rectangle is. If it's a square, then your perimeter is going to be fairly small for the area of 48. But if it's a rectangle that looks like this, then the perimeter is going to be fairly large for that same area of 48 because it's not as efficient in capturing that area. You would need more of a perimeter to capture the same area of 48 if it's a rectangle that looks like that. And since we don't know anything about the rectangle, and just being given the area, I would say, I could have no idea what the perimeter is going to be because that depends on how symmetrical the rectangle is. A square is a type of rectangle. So anybody who tells you, hey, JD, this square is a rectangle, is telling the truth. So every square is a rectangle, but not every rectangle is a square. So squares are a subset of rectangles. And by the way, squares are also a subset of parallelograms and trapezoids. Every square is a trapezoid because what's the definition of a trapezoid? It's a quadrilateral that has one pair of parallel sides. That's it. That's the definition of a trapezoid. And does that matter? If I'm describing a square, could I describe a square in that way? That it's a quadrilateral that has one pair of parallel sides? Yeah, that would still be true for a square. It has another pair of parallel sides, and also each pair of sides is equal to one another, and also all the sides are equal. So there's a lot of other things that are true of a square, but it's not incorrect to say that a square is a trapezoid. I think we're ready for statement 1 on its own. Let's just eliminate B and D. Statement 1 on its own says that each diagonal of the rectangle has a length of 10. Does knowing the length of the diagonal allow us to infer the sum of the length and width And there are two ways we could do this. We could do this algebraically using the Pythagorean theorem. We would say that, statement 1 is giving us the square root of L squared plus W squared. And then we can square both sides and say the sum of the squares is 100. So we could do that algebraically and say, okay, now that I know the sum of the squares, can I infer the sum of the original values before they were squared? And I think a lot of people would probably get this wrong. A lot of people would probably say, yeah, if the sum of the squares is 100, then the sum must be 10, right? They would just say, basically the mistake that people would make here is they would say that the square root of this is this. And they just take square root of both sides of this, or of both terms. But that is not correct. What would be correct? Like, what is the square? If you were to square L plus W, what would you get? If we were to square the sum, you would get L squared plus W squared plus 2LW. This we get from S2.
L and W, yes.
But we're not looking at S2 now. You're about 2 minutes ahead of where we're going. Without S2, just statement 1 on its own, we can't answer the question. And we just saw that algebraically, right? Because we would say, well, I don't know what this term is. All I know is that this is 100, but there's a missing term. Is there also a way to kind of prove to yourself visually that statement 1 is not sufficient on its own? Visual, I mean something like this. Like you'd say, okay, here's one rectangle whose diagonal is 10. And here is another rectangle whose diagonal is 10. And you can tell me if you think I did a good job or not of making these black lines approximately equal. I think I did a terrible job, didn't I? I think this square would have to be like way bigger, right? Let's try this. So here are two cases. And you see how I'm always going for extreme cases, right? One is a square and the other is a really skinny rectangle. So you see the black lines look like they're approximately equal. But if we were to figure out the perimeter, the perimeter of the square is much greater than the perimeter of the rectangle. And you can put an even finer point on it by squishing that rectangle even further. So that, I mean, if the rectangle is sufficiently squished, then the diagonal is equal to the length. And the perimeter would actually be double the diagonal. So you can kind of prove to yourself visually that statement 1 is not sufficient on its own, or you can do it algebraically with the special product, right? So saying, hey, the square of a sum is not the same thing as the sum of squares, and therefore statement 1 is not sufficient on its own. We don't know what the area is with statement 1, right? But we know that the diagonal is 10. So what you want to do is draw two different rectangles that have the same diagonal, and then ask yourself, would they have the same perimeter? And what I'm saying is, look, if you sufficiently squish this rectangle, eventually what will happen is that the perimeter of the rectangle is exactly twice the length of the diagonal. With a sufficiently squished rectangle, your perimeter would be 20. Because because this part, the width would be 0 in the extreme, right? It would be like 0.00000001. And your diagonal would just be the same line as your length. And then the perimeter would be twice the diagonal. So in an extreme scenario, the perimeter would be 20 for a diagonal of 10. But in the other extreme, if it's a square, then the perimeter would obviously not be 20. Why? Because, I mean, look at what the diagonal of a square looks like. You can see here that the perimeter is not double the diagonal. Can you see it or no? I mean, if the perimeter were double the diagonal, what would that mean? That would mean that this line is equal to the sum of these. But we know from triangle theory that a side of a triangle will never be equal to the sum of the sides. It will always be shorter than the sum of the other two sides. And what happens here in the extreme is that it's no longer a triangle. So what we're doing when we're squishing the square is this triangle eventually becomes not a triangle anymore. It's just a straight line. That's right. If we knew the slope, if you knew this angle here, then you would be able to draw the rectangle, right? Because you know the length of the diagonal and you know the angle of the diagonal, then you can draw the whole rectangle. There would be no more missing information. We would know everything we wanted to know about the rectangle. But since we don't know the angle, maybe it's an extremely squished rectangle where the angle of the diagonal is close to 0. Or maybe the angle of the diagonal is 45 because this rectangle is actually a square. And those would lead to different answers, different perimeters. With a square, the perimeter would be much bigger than twice the diagonal. But with a rectangle whose width is approaching 0, the perimeter would be approximately double the diagonal. Because the diagonal here is basically equal to the length, and the width is basically 0. So the perimeter would be double the diagonal. But here it's much more than double the diagonal. So for a given diagonal of 10, you're going to get different perimeters depending on the shape of the rectangle. Hey, I'm just going to interrupt my own video for a moment here. If you're finding value in this video, please let me know in the comments below. And give this video a thumbs up. It really motivates me to keep uploading a new video every day. Alright, back to the video. So we're finally ready to combine the statements. And with both statements combined, if you know the diagonal and you know the area, the easiest way to solve it at that point probably is to say L plus W squared is L squared plus W squared plus 2LW, and then take the 10 for that part, turning it into 100, and take the 48 for that part, turns that into 96. And then you would say, this is 196, and therefore this is the square root of 196, and we're done. So that's the easiest way, I think, to solve the question at this point. When you combine the statements, is to just do a little bit of algebra and show yourself that yes, I can find the sum of length and width. And by the way, just as I suspected, we don't know what the length is and we don't know what the width is. We just know that their sum is 14. It's exactly the way Eric said it. If I tried to mess around with the shape of the rectangle now, if I want to keep the diagonal the same, but start squishing the rectangle, I'm going to impact the area. The area won't stay the same. And if I want to keep the area the same while squishing the rectangle, the length will have to change. I can't keep one of them the same while changing the other. Now that's, I think, a bit harder to prove to yourself visually, which is why I defaulted to algebra here. I think if you do know, if you really understand intuitively that rule about the efficiency of the perimeter for a given area, then that can help. But I would probably, for combining the statements, I would probably encourage people to just do a bit of algebra. I hear what Deepanjan is saying. He's saying if I'm familiar with the Pythagorean triple 3, 4, 5, I can kind of make the observation that if the diagonal is 10, so scale factor of 2 for that triple, then we're dealing with 6 and 8, and it just so happens that the product of 6 and 8 is 48. And then you don't have to do all of this algebra that I did here. Is that what you're saying, Deepanjan?
Yes, when I looked at statement 2, I could see that 6 times 8 is 48, but I didn't know, right? It could also have been 48 times 1. But then when I looked at statement 1 again, it sort of clicked.
Yeah. So the only danger there with the observation is that maybe there's another pair of numbers other than 6 and 8, such that the product is 48 and the sum of the squares is 100. If you do the algebra, you're proving that there isn't, that this is the only pair. With this, it's like, okay, I found one case that works, but am I convinced that there doesn't exist another case that works? I don't know. So for data sufficiency, finding one case that fits doesn't actually solve the question, because of course there's going to be a case that fits. The question is there more than one case that fits? By default, we know there will be at least one case that fits, so finding a case that fits doesn't actually help us. What helps us is proving that it's the only case. Good observation. So if we had an integer constraint, the sum of the squares of two integers is pretty limited. And to your point, there's only one pair of integers whose squares sum up to 100. I can't think of any other way to get to 100 by adding together two squares of numbers other than 36 and 64, right? Because 25 would require 75, which is not a perfect square. 16 would require 84, which is not a perfect square. 9 would require 91, which is not a perfect square. 4 would require 96, which is not a perfect square. 1 would require 99, which is not a perfect square. And going in the opposite direction, 49 would require 51, which is not a perfect square. So yeah, unless you can use 0 squared and 10 squared, which we can't, right? So if you had a constraint of these are positive integers, then yes, statement 1 would be sufficient on its own. But statement 2 would not be sufficient on its own. Why? Because it could be 6 by 8, or 4 by 12, or 1 by 48, or 3 by 16. So then the answer would be A, if we were told that the length and width are integers. If you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.